Thank you very much. Welcome, everyone. My name is Konrad Clapa. I'm representing the Technical University of Łódź, but also the company Eviden. So what I'm going to present here is the research I'm doing as part of the implementation doctorate. So it's joint venture between Technical University of Łódź and a company I work for, Atos and Eviden. So it's like there are two entities. Myself, obviously, I'm implementation doctorate PhD candidate, but I'm also working for Atos in the area of cloud, mainly public cloud, but also hybrid. So in my day work, I'm basically designing the systems for our customers where they can run workloads both in the cloud and on-prem. So over 17 years of experience in the industry. I've been mainly working in the research and development part of the company, and I'm very much connected to the community of Google Cloud. So I'm also a leader of some communities, developer expert communities in Bydgoszcz and previously in Łódź as well. Okay, so as part of this work and this research, you can actually find already some articles that we created. They're mainly about setting up the lab for doing this research. So we have one article that was published by Technical University of Łódź, but also in Springer. And also we have we co-authored 2 books on Google Cloud Platform, where you can find information about running workloads, machine learning workloads in Google Cloud and on-prem using Google Distributed Cloud. Okay, so that's it about me. We're progressing with the research according to the plan. We actually had to extend it a little bit, but what we have done, we have went through the literature study. So we've been trying to understand what is the gold standard for running machine workloads on-prem. So that has been done. We identified the state of the art. We have built virtual and physical lab for doing our research. We have performed example simple data manipulation, but also we have selected the machine learning models that we want to run on this lab. And we tested 2 methods of making this more efficient. So basically it was about scaling the nodes, which is obviously not something that the industry will be accepting. And we were trying to find out other methods to do it. So the other methods I will be showing today is the changes of the characteristic of the scheduler of Kubernetes. So let's go to the problem statement. So basically, as you know, now we have a lot of machine learning models that we can run directly in the cloud. So the problem of having the right resources in place and efficiency of that, we somehow outsource it to the cloud provider. But there are situations where we need the data sovereignty. So basically, we don't want our data to go out of our data center, factory, wherever we store that data, and we want to process it locally. The other factor is the data locality, the speed of processing this data. And we obviously don't want to be dependent on cloud providers. So the solution for that is that we can actually run those workloads locally, close to the machines, close to the source of the data. But we need the resources, yeah? And machine learning workloads are pretty resource intensive. And we want to spread that workload between different nodes. So what we're trying to do is to maximize this effectiveness with different methods. So this is pretty important topic for the industry, but also for the science world, for the scientific. There are dozens of articles that we have found that are talking about how to improve this efficiency. But also we see hundreds of industrial cases with our customers where this machine learning needs to run locally. We have identified that actually loads of companies, big techs, are working on that, especially in the area of scheduling GPUs. So IBM, Google, Atos, also NVIDIA, Alibaba Cloud. So there's lots of research that are concentrating mostly on optimizing the scheduling when we use GPUs. Okay. When we started this research, also the analytics said that this is where the industry going for, so containerization using cloud native technology, but also running those workloads locally. There's 75% of the applications in the enterprises will be using some kind of AI. And I think those predictions from the past are coming into realization. Okay, so where is the edge? This is pretty difficult to define what is the edge. Well, I don't think there is a simple, there are lots of definitions, but basically I would say that the closer to the data it is, the better. So edge devices you can find in autonomous shops, you can find it at the airport with the robots that are using artificial intelligence locally. You actually, one very interesting thing is that the longest bridge in the world in China is actually being monitored using Kubernetes and actually distributed Kubernetes on the edge. So that's the picture. Obviously, autonomous cars and even submarines. So submarines are a really good example of where we want to have disconnected edge devices, because obviously there you cannot make sure that you have connectivity to the cloud, right? So you need to perform all those computations locally. Okay, ourselves in Atos, we do build servers as well. So I just wanted to show you that edge, it can be a small Google Coral kit or Raspberry Pi, but edge is also considered as an extension of the data center that is very close, especially in telecoms. So it can actually be a rack of servers. So when we're talking about edge, we need to take into account all those types of devices. Okay, so jumping up to the point, how we're solving the machine learning task, how we are executing the machine learning task within Kubernetes, within cloud native systems. So basically, we're containerizing the workloads. So if we look at this system, we basically have inputs. So we have our data sets that are labeled. This is defined into pipelines. Then this pipeline is, every container is actually a job that will be scheduled on the hardware on multiple nodes. And then once the pipeline is fully executed, we can serve the model. Okay, so the state of the art today is pretty clear. This is Kubernetes that is used for scheduling containerized workloads. There have been multiple other technologies that have been on the market, but currently the state of the art is Kubernetes. So that's why we selected Kubernetes stack to run those workloads and try to research how we can make this more effective. Okay, so this is a particular machine learning pipeline. So what we would usually do is to inject the data, transform the data, train the model, validate and test the model, and finally serve it. So what we are actually doing, every job, which might be Python, Python script, or it can be written in any other language that we like. We take that code and we put it in a container. And this is a discrete job that's going to be scheduled on the orchestrator. So orchestrator gets this workload, and basically its job is to make sure that it lands on the right node of the Kubernetes cluster. Okay, so this works both with the experimental phase, but also with the production phase. So basically, Kubernetes is going to be able to be used both for experimentation and for production. So in production, we can train the model, but if we need to fine-tune it because we have additional data, this is also possible to be done. Okay, so our research plan was obviously the first phase. We needed to find some baseline to compare, once we find a method, how we can improve this efficiency. So we started with very simple calculation, because we unfortunately found out that Kubeflow running on Kubernetes. So that's the software that's used for machine learning operations and creating pipelines. It wasn't very stable, so we wanted just to make sure that we have the proper baseline. So that was quite a challenging engineering task. But finally, once we made it stable, we created the baseline with very simple calculations. We realized we need to go a step farther. So we decided we're going to use the MNIST data set that is basically used to recognize handwritten digits. So that was the workload that we decided we're going to run to define the baseline for our experimentation. So this is basically using Vision AI. And finally, once we have it, we want to compare it with other models and document the proofs. Okay? So this is the lab. The initial lab was purely a laptop because Kubernetes is a software solution. So we started using a laptop with Ubuntu virtual servers. On top of that, we have used the K3s distribution of Kubernetes, which is very much targeted on the edge implementation because it has very, very small footprint, and that's what we were all about, to make it small. But we just realized that there is a lot of noise coming from different processes running in that laptop, so we need a bare metal solution. So we decided to purchase nodes. These are Intel Nuke nodes, where we make sure that there are no other noises coming or processes that are disturbing the research and the calculation. So we ended up having this 4-node cluster. This one node is a control node, so it's actually not taking, it's collecting the data. It's not actually taking part in the computation. And this is the Kubeflow. So we basically have a console. This is a software solution where we're actually defining the pipeline. So this is where we are defining the machine learning task that will be executed. Okay. And for the purpose of collecting the data, we have created a custom benchmarking script. So this basically is talking to Kubeflow API. So the pipelines that I was talking about. So MNIST pipeline, which is actually basically transforming the data, creating the model, and then evaluating the model. This is defined in a YAML file with the Python code that is needed that uses TensorFlow to perform the machine learning calculations to execute the algorithm. This is defined in a YAML. We put that YAML into the Kubeflow, and Kubeflow is basically executing the task on Kubernetes, and the scheduler is scheduling those workloads. What we have also done, the first thing we wanted to see is what is actually the components of the time needed to execute. So what is the first one is the creation. The first time is the time that is needed to create the pipeline itself within the system. Then we have the execution of the pipeline. So this is where the code is executed. Then we're retrieving the information and we're deleting the pipeline. So the system is ready to onboard next task. Okay, so what we decided to do is to have 1 to 3 node Kubernetes cluster and execute from 1 to 30 parallel execution. So we wanted to have this system loaded with much more workload. So this MNIST was actually executed from 1 time to 30 times exactly the same task. And basically it was generating the model to distinguish the digit numbers. Okay, so we realized that, as I was showing, there are multiple factors when it comes to time that is being calculated. So the largest component was definitely the execution time. So the creation, if you see that 90%, well, depending actually on number of executions, but 90%, we can say that majority of this time is taken for executing the pipelines. As we go and we have more and more pipelines being executed, the time that is for creation, retrieval, and deletion is higher, but we're talking here about 1% of the actual total time. So we decided that we're going to concentrate purely on the execution time. Okay. Okay, so the next step for us was we've been actually testing here. We've been testing different number of nodes. We started with 1 node, 2 nodes, and 3 nodes. But basically, it's not going to help us just to increase the number of nodes, right? Because we want to have actually the at the edge, no one is going to come and add and remove nodes as we go and as we create tasks. So we decided we need to look for tuning this somewhere else. So we've been looking at what is being done by others. So basically, there's loads of researchers on scheduler where they're created custom schedulers. So for example, there is a Volcano scheduler. I believe that's created by Google. But basically, all this is working on GPUs. So it's rather for a data center where we have big tasks. Or for example, the workloads are being scheduled together. So you need to, all the containers that you create, you need to tag them. So for example, the flow of data doesn't need to go outside of one node to the other node. So we decided that we're gonna look at how we can do the same, well, not exactly the same, but how we can make sure that we have very small footprints and the nodes have only CPU available. And what we looked at is to how we can change the characteristic of the scheduler mechanism. So the scheduler basically, how does it work? The pipeline with the task that I was showing is going into Kubernetes. There is a scheduling request. Scheduler understands he needs to put this workload somewhere on one of the nodes. It would get the utilization of those nodes, whether it's CPU, memory, it can be network utilization. That's for us to decide. We started with CPU because those workloads are very CPU intensive. It's getting this data and it's calculating the score for these nodes where this workload should be scheduled. And this is something that we can change. There is a out-of-the-box scheduler that will try to distribute the workload evenly, but we decided to play a little bit with the characteristic. So for example, we can change the characteristic. So the nodes that have the lowest utilization, they will get the least score. So we will try to bin pack everything into one node, then to the other node, and so on. So this can be modified however we want. So we have selected multiple of those and created some tests. So once this scoring is done according to the function that is defined here, node is selected, and this workload is put on that node. We're waiting for another task, and once this is finished, obviously those resources will be empty. But we will have multiple pipelines, so the scheduler needs to understand and do the calculation when to put next task, because this task might not be finished before the other tasks are already finished. Okay, and those are on the right-hand side. This is what we actually want to, we're analyzing and we want to publish. So our different characteristics, those are pretty random right now because we need to understand if this is actually affecting the times. But we do already see by changes of those characteristics, we have differences in the time execution. So if you see, this is the baseline that we have here. It can either get better or worse. So we see, and depending also on the parallelism, if when we start, those differences are not that visible, but as we go, we can definitely, sometimes we see differences of 25% in the total time execution. Okay, so this was done for MNIST, and we realized that we just can't work with a single machine learning algorithm. So we have selected additional data sets that we want to work with and different machine learning algorithm we want to use. So we want to extend, we actually have already the pipelines created, but we need to execute this experimentation. So we're going to work with other convolutional neural networks. So this is CFAR10 images of different objects. So that's going to be another machine pipeline. It's going to be much more challenging task, and it's much more computer intensive. We have clustering k-means with large tabular data set. So this is basically, we have a data set from Walmart where we are going to analyze that. We have sentimental analysis with a database of reviews from customers. We're going to use some clustering with the base of COVID-16 symptoms. We want to have an ECG time series. And finally, we are also looking at X-rays for pneumonia. But this is very compute-intensive task, so we're not really sure if this will fit into the nodes that we have. So we need to check whether this will be possible to fit it in. Okay. The other step is to just use other type of devices with the smaller footprints to go up to the Raspberry Pi size compute nodes. We didn't start with that in the first place because the processors that Raspberry Pi is using were not supported by the software stack, but now it's supported, so we want to try that. And also we want to use non-homogeneous hardware to see how it will be, how the changes of that characteristic will affect it if we don't have homogeneous hardware. Okay. There are some references that I guess the presentations will be shared later on. So we can have a look at that. You also can have a look at the articles that we published in the past. And with that, I want to thank you for listening just before the lunch. I'm waiting if we have any time for questions.